Slices are the dynamic arrays of Go. A slice is like an array list in Java, vector in C++, or vec in Rust. Let's start off by taking a look at some of the differences between arrays and slices. Unlike arrays which have a fixed length at compile time, slices have a variable length, meaning we can add or remove elements at runtime. And while the type for an array includes the exact amount of elements contained, the type for a slice is just a pair of empty square brackets followed by the type of its elements. Another difference is that it's possible for an array to be comparable if and only if the type of its elements t is also comparable. Comparable arrays can be compared using the comparison operators and can also be used as keys in a map. On the other hand, slices are never comparable. And lastly, but also importantly, Go is a pass-by-value language as opposed to pass-by-reference. So what happens when each of these types gets passed into a function as an argument? Well, in the case of an array, all the data is copied, whereas in the case of a slice, only the pointer to the data is copied. So if you're planning on passing around large amounts of data, you should either be using slices or passing an array pointer to avoid unnecessary copying of data. To understand why only a pointer to the data is copied for slices, we first need to understand what slices are. We can think of a slice as a struct with three fields, the first one being a pointer to the start of the elements in the slice, the second one being an integer representing the length of the slice, and the third one being an integer representing the capacity of the slice, or how many total elements can be contained within the slice without requiring another memory allocation to grow the capacity. In fact, this is the exact representation of a slice named SliceHeader in the standard library package named reflect. Although, as of Go 1.21, this struct is deprecated in favor of the new unsafe.slice and unsafe.sliceData functions. Also, a quick note here, especially for Go beginners, is that the type of data, uint pointer, is not a regular type-safe pointer in Go. It's just a pointer value, meaning that it doesn't count as a reference, and because of that, the data that it points to could be garbage collected at any point. A regular pointer in Go to any type t is just *t. Moving on, the Go programming language comes with several built-in functions which you can use without the need to import any package. Several of these are useful when it comes to creating, reading, and updating slices. Let's start off by taking a look at how to create a new slice. There are three primary ways to do this. For example purposes, I'm going to be working with a slice of integers. The first way to create a new slice is through a normal variable declaration, var, slice, and the type of an int slice. This will create a zeroed out slice with a length and capacity of 0, and a data pointer pointing to the memory address 0. This slice is commonly known as the nil slice. The second way to create a new slice is through a short variable declaration, slice : the type of an int slice, and empty curly braces. This will create a slice almost identical to the nil slice, but instead of the data pointer going to the memory address 0, it points to a special address that represents a zero-sized variable. For example, an instance of the empty struct also points to this memory address. It's also possible to specify initial values of the slice in between the pair of curly braces. Without any initial values, this slice is commonly known as the empty slice. Finally, the third way to create a new slice is by using the built-in function make. For example, slice : make and pass in the type of an int slice. This will create an empty slice similar to above, but the make function also supports additional arguments. We can specify the initial length of the slice as the second parameter. The elements will be initialized to the slice type's 0 value, in this case the integer 0. And we can also specify the initial capacity of the slice as the third parameter. Go will allocate memory up front for you to store elements up to the capacity. Specifying the capacity here is extremely useful for performance if you're going to be storing large amounts of data. It's also possible to specify a combination of these two parameters. Go also comes with another built-in function named new. If we call this function with the type of an int slice, it returns a pointer to a nil slice. Similarly, if we want to create a pointer to an empty slice, we can just use the ampersand operator. Overall, these are the 5 most common ways to create a new slice or slice pointer. Next, let's take a look at how to read from a slice. Given an integer slice s with 4 elements, we can get the length of the slice by calling the len function, and we can get the capacity of the slice by calling the cap function. To iterate over the slice, we can create a simple for loop with the variable I, starting from 0 and going all the way up to less than the length of s. We can also print these values by calling the printline function in the format package fmt. If we're iterating through a slice front to back, we can also use the range form of a for loop. Range also returns a copy of the value at index I as the second value. We can then just print v, and we'll also have to rename I to underscore since Go is strict about unused variables. Now, let's take a look at how we can modify slices, starting with adding elements. Let's say we have the same slice s from before, with 4 elements, and we want to push the integer 5 to the end of the slice. We can do this by calling the append built-in function with the original slice s and the new element 5. The return value of append is a new slice containing 5, so we'll need to make sure to also reassign s to this value. Let's dive into what happens behind the scenes here. When we initialize s, a new slice is created with a length and capacity of 4. Then, when we call append, the Go runtime checks to see if there's enough capacity for the 5th element. In this case, there isn't, so it performs a reallocation. New memory is allocated with twice the original capacity. In this case, it goes from 4 to 8. All of the previous elements are copied over, and then finally, the next available space is set to 5. A new slice header is created with the updated data pointer, length, and capacity. We then reassign s to the newly created slice header. This is why it's important to specify the capacity when creating a slice in the case that we are storing lots of data, so that we can reduce the amount of reallocations required and thus improve performance. Also, append is a variadic function, which means we can pass in multiple elements as arguments to the function. Now that we know how to add elements, how can we remove elements? Well, it's possible to remove elements from the front and back of a slice by using the slicing operator. If we have the same slice s again, we can pop from the front of the slice with s square brackets 1 colon, or pop from the back of the slice with s square brackets colon length of s minus 1. Pop front will be a slice with length and capacity of 3, and pop back will be a slice with a length of 3 and a capacity of 4. With the slicing operator, you can specify the starting and ending indices, separated by a colon, to indicate the elements you want included in the new slice. For example, if we want to get to the middle 2 elements of s, we can do s square brackets 1 colon 3. This will create a new slice with the data pointer 1 index ahead, a length of 2, and a capacity of 3. You may have noticed some interesting behavior related to the capacity. Whenever we remove elements from the end of a slice, the capacity for those elements remain. It's easy to run into problems if we aren't aware of this. For example, one could assume that calling append on the middle slice with the integer 5 would allocate a new slice. However, since the middle slice has a capacity of 3, which is enough for the new integer 5 to be added, the length is increased and the underlying data is overwritten. To prevent this, there is actually an optional third parameter to the slicing operator which we can use to limit the capacity. We can add colon 3 inside the square brackets to stop the capacity from extending past the start of the third index. Now, any calls to append elements to the middle slice will trigger a reallocation. However, if we change the first element of middle to 6, that value is changed for all the other slices too. That's because a slice is like a view over an underlying array, and currently, all of the slices we have point to the same section of memory. If we want to prevent overwriting data altogether, then we will need to create a brand new slice containing the same data. Thankfully, there is a built-in function named copy made just for slices. To make a copy of s, we first need to create a new slice with the same length as s. Let's name this scopy. Then, we can call copy and pass in the destination and source slices. Go will copy elements until either all of the source is copied from, or until all of the destination is copied to. Keep in mind, copy only looks at the length of a slice and not its capacity. In the end, copy will return the amount of elements that were copied. Another topic you may run into when dealing with slices is sorting. For this case, Go has the sort standard library. We can quickly sort a slice of integers by calling the sort.ints function and passing in s. This will sort the slice in place. We can also sort floats and strings by using sort.float64s and sort.strings. But what if we want to sort a slice of a different type? Well, we could use the sort function in the sort package, but let's use the brand new standard library package named slices. This package was released in Go 1.21 as a follow-up to generic types being added to the language a few versions prior. We can sort our integer slice s by calling slices.sortfunc and passing in the slice s, along with a compare function that returns a negative, positive, or 0 integer. Although, since integer is an ordered type, we can simplify this to just slices.sort. The new slices package contains several useful functions such as binary search, clone, contains, max, min, reverse, and even though we can't use the comparison operators on slices, we can use the slices.equal function instead. We can see that all of the functions in the sort package have their generic equivalents in the new slices package. That's it for this video. Thanks for watching, and I will see you in the next one.